Okay, welcome to Lab 9. This is Sean. And in today's lab, we're going to continue learning a journalistic approach to data analysis in R. Today, we're going to really dig into exploring relationships between two things using both some graphs and some statistical tests and some more basic descriptive statistics. This lab is going to function the same way all prior labs have functioned, in that I've written some code. You're going to write along with me. Uh, there will be times when you're going to see the word task in blue, and I want you to write your own code. Um, in general, the first half of this lab you'll be doing along with me. The second half you're going to do on your own. There's a lot of good cheat sheets here, many of which were linked previously. We are going to be using one new package today, and I've linked to the cheat sheet for that. It's called Core with three R's. It's for correlations or looking for relationships between things. Uh, so the way this is going to work is you're going to create your own version of this Markdown file and upload it to your Git repo, and then ultimately you're going to submit it after you push it to Git on Elms. Okay, so we're loading 6 packages today. We're going to load the tidyverse like we always do, and Janitor for data cleaning. You're going to load the Arcos package from the Washington Post to get opioid data. You're also going to load the Tidy Census package. This is for getting census data. And the Scales package for cleaning up access labels. And then, as I mentioned above, you're also going to load a new one, which is the Core package, CORRR. And it's a way of doing some nice correlation testing, a little bit better than the base R package R code allows. So go ahead and load those in the block here. You may need to install them if you haven't done that. Uh, okay, so we're going to learn to examine relationships at first by examining the relationship between the rate of opioid pills that were sent to counties across the United States uh, and compare that with the death rate from opioids in that community. Uh, so a lot of this is sort of intellectually inspired by a story the Post did last summer in July, um, where they looked at how opioid death rates um, uh, compared uh, with the rate of pills as they were shipped to those communities. And what they found was that in places that got a lot of opioids, adjusted for population, had higher rates of opioids per person in that community, more pills per person. Death rates also soared. There were a higher rate of people dying per unit of population. Um, and so we're going to dig into a little bit about the method they had. You're actually going to read this for uh, this week. Okay. Um, so the first thing we're going to do is we're going to load the data that we need. So we're going to load a couple tables that we have previously worked with from the Arcos database. Again, the Arcos database is the Washington is a database that the Washington Post and the Charleston Gazette Mail got by uh, after a lengthy legal battle with the government to um, uh, to get this data set of shipments of um, billions of opioid pills between 2006 and 2014. Uh, there's all the documentation. So the first thing we're going to do, we're using the Arcos package from the Post to get this. This is an R package they created to pull in data. So we're going to store our key, which is our password to get, essentially our password to get data. And we're going to pull in 2 data frames. So the first is the number of pills per year per county. So I'm using the summarize county annual function. I'm giving it my pass key. and just cleaning up the column names when they come in to lowercase them, standardize them. And then I'm also from Arcos pulling county population per year. So I'm just going to run both of those, and they'll both come in. Let's just take a quick look at that. So again, we've got one value per county per year, and we've got a count. This is the number of shipments. Dosage unit, essentially a proxy for the number of pills. And then we also have population. So one record per county per year with the total population in that year. Okay. All right. Now we're going to put them together into a single table, and I'm going to run the code here, and then I'm going to pop up the table, and then we'll walk through what it does. So here's this new table called pills population, and it has one record per county with the average number of pills sent per year to that county over the 2006 to 2014 period. So one value with an average per year, one value with the average population each year, and then it takes these two numbers here, these two columns, and uses that to compute the average pills per person for that county. So in some counties, these may look familiar, like Mingo, West Virginia, there were 179 pills per person on average over that period. Compared with some other places, just, much smaller levels. Okay, so how did I do that? Created a new object called pills population, and took my Arcos County population per year data frame, that's this one, and I joined it to pills per year. I joined it on a number of fields: the county FIPS code, the unique identifier for each county, the year, the buyer county, and the buyer state, the name and the state. Then I grouped by county FIPS, the FIPS code, the county unique identifier code, buyer county, and buyer state. And I calculated the two new columns that appeared there. So I took the average, I created the average pills per year column by calculating the mean of the dosage unit. Remember, dosage unit is a proxy for pills. And the average population per year by taking the mean of the population. Then, after I created those two things, I created a new column called average pills per person, in which I divided the average pills per year by the average population per year and rounded it to 2 decimal places, which is how I ended up with this column here. And we're going to use this one several times today. Okay, now we're going to load and clean the data that we need to describe the death rate by for each county related to opioids. So I scraped this from the CDC. So here it is as a tab delimited text file. It's in your data folder. And I've also included a README that explains what it is and how I got it. So I would encourage you to read that README for the full, full breakdown. But it's essentially the number of deaths per 100,000 population over that period. And in its raw form, it includes a number of things that we'll look at when it comes in. So one thing to note about this data is that we actually don't have the opioid-related death rate for each of the every single county in the U.S. Part of that reason is that uh, the way the CDC computes those figures from its data set tracking deaths, uh, there uh, there may have been too few deaths, and so there are privacy concerns about reporting out that information, or the statistical sampling method they use may be sort of unreliable. So just going to read this in, and here it is. And so what do we have here? We've got the unique identifier, the county code, and the county name and state, the number of deaths, and the age-adjusted rate. So they've made some adjustments to account for um, statistical variations related to age that might skew the death rate in places with unequally distributed age of population. So when I read this in, I used the read TSV function, cleaned up the names. I filtered out the places where the data contained missing values or unreliable values. So I basically said here, look for, instead of where it says a number in age-adjusted death rate, the words unreliable, this pipe means or, suppressed, or missing. Filter those out and only return those that have a number. Um, and then I converted the column types to numeric, just so we can work with them later. Okay, so we have about 1,000, right? Which is different than the 3,000 um, counties for which we have information on the number of pills shipped to those places. So the analysis we do looking at relationships is really only going to have um, be for these 1,000 counties where there was reliable data. They tend to be the larger, more populated counties. Okay, so now we're going to put them together. So I'm going to join my pills population table. This is the one with the rate of pills per person with the opioid death rate table. Okay, so we end up with this one table of 1,066 counties that has the county code, county name, the state. We've got the pills per person rate. This is what we really want to focus on here. And the age-adjusted death rate. So what we're really going to be looking at as we go forward is there anything that we can see in terms of whether or not the um, the number of pills sent to a place, is it all related to the death rate? Do we see places that got more pills per person have higher death rates? And vice versa, actually. And we'll walk through that in a second. Okay, so yeah, so the key question guiding our analysis here is, in communities that received more pills relative to population, did more people die of opioid-related deaths? We could also ask that question the other way. In places where people died of opioid-related deaths at a higher rate, did they get more pills? Um, this is pretty important here. What we're not doing in this kind of analysis that I'm about to describe is establishing a causal relationship. We're not saying that places that got more pills caused more people to die. We haven't really done the work to do that, and there may be a host of other factors to go into it. But from a news perspective, it's still, I think, interesting in determining whether or not there's some sort of general pattern here that we could use to go ask more probing questions to flesh out a story. And certainly the Post in this piece, um, we're able to show that it was many of the same places, right, where the opioid death rates were highest that also got the same number of pills. We see that in West Virginia, We see that in parts of Oklahoma. We see that in parts of Nevada. Um, there are exceptions, but we saw this over and over again. It's a really powerful way of showing the potential harm here. So there's a bunch of different ways we can look at this question. One is um, we can take all of the 1,000 counties we have and group them into buckets based on their the number of pills sent to a given place, and look and see whether there's some variation in the death rate that way. So we're doing that here. And actually, we're doing it the other way. We're grouping it into buckets based on the death rate and looking to see if there's some variation in pills per person. So I'm going to run this, and we're going to talk about what it shows, and then I'm going to walk you through the code that produced it. Okay. So what I've done here is I have taken all 1,000 counties and grouped them into, sorted them based on their death rate, and then grouped them into 5 buckets so that the counties with the most similar death rates are lumped together. So we see that here. We're calling these quintiles. Quintile would be a group of 5, each accounting for about 20%. So in this case, each quintile is going to have about 200 counties in it. A quartile would be 4 groups, each with about 250 counties in it. So what I've done is first I've taken the average age-adjusted death rate. So this first group of 200 counties, the lowest 200, have an age-adjusted death rate of 3.5 deaths per 100,000 population. Okay. At the other end, the sort of highest 200 counties have an age-adjusted death rate that is much, much higher, 21 opioid-related deaths per 100,000 population. Okay. So what I've then done is I've also computed for each group the average number of pills per person sent each year over that 2006 to 2014 period. So this lowest group with the lowest death rate got about 33 pills per person per year over that period. Whereas the group with the highest death rates, the places where the highest proportion of the population died because of opioids, got many more pills per person on average, closer to 70. It's almost twice as much difference here. And we see as we go, as the age-adjusted rate goes from 3 in group 1 to 6 in group 2 to 8 in group 3 to 11 in group 4 to 21, right? It's slowly climbing. We see a similar thing here with the average pills per person, going from 33 in group 1, 37 in group 2, 41 in group 3, 49 in group 4, to close to 70 in group 5. So pretty interesting pattern there. Something that I think would be worth bearing out further reporting. We can, before I move on, I want to walk you through the code there. So we take our death rate pills table, that's this, right? The one that's got the age-adjusted rate and the average pills per person. Because that was grouped, we wrote an earlier function where we created this table by grouping another table. We got to ungroup it. Then I'm creating a new column here called quintile, and I'm using mutate. And I'm using a new function that we haven't used yet. It's called ntile. And an ntile takes 2 arguments, 2 things I need to feed it. The first is which column we are creating our buckets based on. And then we're saying how many buckets. So I'm saying create a new column called a quintile. And uh, how are we creating these columns? Well, we are uh, taking the age-adjusted rate and we are assigning it a group based on that. So I'll just run up to here just so you can see that. So you see it's create a new column called quintile. Baldwin County goes in quintile 2. Escambia is in quintile 4. So it's just about grouping it into buckets. Then I'm saying group by quintile. So we want to put all of the quintiles together and calculate the age-adjusted rate, calculate the average age-adjusted rate. So that's how we know it's 3 for quintile 1 and 21 for group 5, and the average pills per person, also by using mean. Okay. We can also make a scatter plot to explore the relationship between two variables. So we've created scatter plots in earlier courses. I'm going to go ahead and create the scatter plot, and then I'll walk you through the code that did it. So here's our scatter plot. So we have the death rate on the y-axis. So goes from 0 all the way up to like 85. This is the number of deaths per 100,000 population. And on the x-axis, we have the average number of pills per person. Each one of these dots is a county. So this county got about 90 pills per person on average and had about 70 deaths per 100,000 population related to opioids. This blue line running through it is the line, a trend line or a line of best fit that attempts to draw the neatest path through through this cloud of dots. It's a way of sort of seeing the overall trend line here. So, so how do we interpret this? Well, first of all, we notice that this sort of general cloud of dots here, but more to the point, this blue trend line that's running through it is going up, right? Indicating a positive correlation. We'll talk more about that in a moment. So what that means is as the pills per person rate goes up, so too does the death rate, or vice versa, if you wanted to say that. As the death rate goes up, in general, the number of pills per person to that community also go up. There certainly are exceptions, you know. It's not like every dot is right along this particular line, but there's a general trend there. The other thing is, and we'll talk about this in a minute, but the bulk of these dots are fairly well concentrated around this trend line. Sometimes you see scatter plots that look like somebody just dropped a bunch of marbles on a table and there are dots kind of everywhere. You actually can make out a pattern here. That's going to indicate that there is something of a relationship there, maybe a moderate relationship. Okay, so the code for this, we're saying create a new ggplot with our death rate pills table. And geom_point basically says draw a scatter plot. On one axis, put the average pills per person. On the other axis, put the death rate. All right. Then we're saying geom_smooth says draw a trend line with pills per person and an age-adjusted rate. This is LM or linear model here. We're saying scale Y continuous, scale X continuous. Or essentially this is just cleaning up the data a little bit. And then we're putting some labels on it. Okay. The last thing we can do to really test this relationship is compute more precise values, the kinds of things that are maybe hinted at by the scatter plot. So we're going to compute something called the correlation coefficient, or lowercase r, this is often called, um, that really helps us understand whether or not two things sort of move in tandem or move in some unison, indicating some kind of a relationship. Not causal, just a relationship. Uh, and as we compute this, there's three things I want you to keep your eye out for. So the first is what's called the strength of the correlation. How how meaningful is this? How robust is it? The direction, whether it's positive or negative, and statistical significance, whether the thing we found is a complete aberration, statistical anomaly, or whether there's some potential meat to it. So we're going to use a function from the correlate package, or sorry, the core package, CORRR, called correlate. So what I'm doing here is I'm saying take my death rate pills table. Again, we're going to ungroup it because we created this data frame from something that was grouped. And so it remains grouped unless we ungroup it. And if we don't ungroup it, this won't work. And then lastly, we're going to select only those columns that we want to correlate. So right now, death rate pills contains 9 different things, including the county name. But we want to get it down to just 2. So ultimately, all we want are the 2 things we want to test the relationship between: the age-adjusted death rate and pills per person. We don't want county or any of that stuff. If we leave that in, it's not going to work. And now I'm going to say correlate. Okay. So we have a little table here that has the correlation coefficient. So how do we interpret this number? So the correlation coefficient is right here, and it is 0.615 or 0.62. So the correlation coefficient is always going to be a number between 1 and -1. And again, this number is our way of interpreting the degree to which 2 variables sort of move in unison or along a similar pattern. Just because they move along a similar pattern doesn't necessarily mean it's like worth reporting out, but it's something maybe if you see a result like this, it would be worth doing some additional reporting to see whether there's a story here. So again, the correlation coefficient, always a number between 1 and -1, indicating the degree to which 2 variables move in unison. So the closer the value is to 1 or -1, the stronger we consider the relationship to be. So this is 0.62. Depending on the domain and who you talk to, this could be considered a moderate relationship or a little bit more than moderately strong relationship. In some domains, this would not be strong at all. In this case, I would say 0.62 is interesting enough to sort of check out, and certainly the post did an entire story about this subject. The other thing to look at when we look at the correlation coefficient is direction. So if the number is positive, then that means that an R of 1, positive 1, would indicate a perfect positive relationship. So as an example, if we were testing the relationship between the average age of an area and the percentage of people in an area who get Social Security retirement benefits, we should expect to see a strong positive relationship, as in areas that tend to skew older are going to have more people who qualify for a program designed for senior citizens. At the other extreme, an R of -1 would indicate a perfect negative relationship. So for example, we'd expect to find a negative relationship between an area's median household income and its poverty rate. So the richer an area is, the higher the average person's income is. In general, the lower its poverty rate is going to be. So those things move in inverse relationship to each other. And then in the middle, we have 0, which would indicate no relationship. So in this case, 0.62 is a positive number. And as we saw from this above, that means that as the opioid death rate goes up, so too does an area's rate of pills per person. The last thing we want to look at is statistical significance. You can get an interesting result, but it may not be statistically meaningful. We can examine statistical significance when we do this correlation test by deriving the p-value. The code for this is a little bit more complicated. So the first thing we're going to do here is I'm going to store a data frame called correlation death pills. It takes this death rate pills table, ungroups it, and selects just those two columns, right? The age-adjusted rate and the average pills per person. So I can pop it up. There it is, 2 columns. Then I'm just going to run this thing called core test, which is part of the stats package that comes with base R. And we're saying, give me all of the very detailed outputs for when you calculate the correlation coefficient. So in this case, we're saying from the correlation death pills table, take the age-adjusted rate, comma, or compare it to, from the correlation death pills table, the average pills per person. This $, which we don't use a lot of here because we use the tidyverse so much, is essentially a way of saying the name of the table, the name of the column. Okay, so we run this whole thing. We get this very complicated output that says Pearson's product moment correlation. There are other kinds of correlation. Pearson's is one that we see frequently used. The correlation coefficient is down here at the bottom, 0.62. We calculated that above in something that was a little bit prettier. And we see the p-value here, which is 2.2 e to the negative 16, which is scientific notation for a very tiny number. Lots of zeros, 2. So because our p-value is less than 0.05, in general, we consider this to be a significant result. Again, not saying it's newsworthy or meaningful, just that it is a statistically significant result. Okay, so we walked through that. I'll be online 2 days this week where I can help you through this. I know some of this is a little bit more complicated. This is about as advanced statty as we're going to get in this class. I want you to put into practice some of what you've just learned by attempting to answer another question. Did lower income areas of the country tend to get flooded with pills more so than wealthier areas? So to answer this question, I want you to use the 3 methods we used above to determine whether there's an interesting trend upon which you could build more reporting, kind of flesh it out, see if there's something worthy of building a story around. So the first is you're going to group it into buckets, like we did above, and calculate the average of median income. And I'll show you where you're going to get that in a second, and pills per person. You're going to build a scatter plot with a line of best fit with median income on one axis and pills per person on the other. And lastly, you're going to calculate the correlation coefficient between median income and pills per person. Then you're going to write up a few paragraphs on what you see. Is there a story there? What did you find? So to get started, we're going to load the data we need from the Tidy Census package, and we're going to pull down a table with median income for each county. So again, remember we need to store our census API key. And then we're going to create a table called county median household income. We're going to use the getACS function to pull down median income values for each county. That's what this variable here is. All right. So there's county median household income. So we get this table with the GeoID, the unique identifier for the county, the name of the county, the variables. In this case, this is median income. We get the estimate. This is the estimated median household income value for each county, and the margin of error. Okay. Now you're going to join this to our PILS population table. So we're creating a new object called PILS population income. We're joining the PILS population table to our county median household income table. We're joining it on county FIPS and GeoID. Those are what the two unique identifier columns are called in the two data sets. Just to make things a little bit easy for us, we're going to rename the estimate column to median household income. It'll just make more sense when we're referring to it going forward. And lastly, I'm going to filter out any NA values in our average pills per person column. If we don't do that, then it may prevent things working in the future. Okay, so now you have a table of pills population and income. So we've got our average pills per person, that's this column. We've got our median household income, it's this column. And you're going to work on looking at whether or not in places that had lower median incomes, did those areas get more pills than wealthier areas? So you're going to use the bucket method. You're going to make a scatter plot. You're going to calculate the correlation coefficient. And then you're going to write up what you find below. Okay, thanks very much.